For all those who join now, we'll start at 7:05. So good evening all. Myself Elizabeth. Today we'll be seeing questions related to communication theory. So let's start today's session. This is a question that appeared in GATE 2017. So this question is related to inter-symbol interference. So the question says, in a digital communication system, the overall pulse shape P of t at the receiver before the sampler has the Fourier transform P of f. If the symbols are transmitted at the rate of 2000 symbols per second, for which of the following cases is the inter-symbol interference zero? So, first, before solving this question, can someone tell me when will inter-symbol interference occur? Someone please respond.
Sampling is less than IQ square.
That happens when 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 sampling is less than accurate rate, actually aliasing is happening. But when we send a signal through a channel, so at that case, when will inter-symbol ISI happens? Okay, say I am sending a signal with infinite bandwidth. Assume that I am sending a signal with infinite bandwidth. Okay, through a channel which is having finite bandwidth. Then what happens to my signal? A signal which in Sadat, could you repeat?
The signal gets filtered.
Okay, actually, it's not the correct terminology. What happens is that the signal's bandwidth gets limited because the channel is having only finite bandwidth, right? And the signal is having infinite bandwidth. So the signal's bandwidth gets limited. So when you limit, like when you limit the bandwidth, that means you are distorting the signal, right? So see, in frequency domain, you are limiting the bandwidth. So what happens in time domain, the signal gets stretched, right? So if the signal is of duration ts in the time domain, then its duration gets more than ts, right? Is it clear?
Yes.
Okay, so that is one way that ISI occurs. So what happens if a signal with finite bandwidth happens? Still, there is some distortion happens. So ISA will occur in the signal. So to avoid this ISA, we need to choose when we send signal, we need to choose the signal's shape appropriately so that we can prevent this ISI. So that is what is called pulse shaping. So to prevent this ISA, this Nyquist has given a criteria which is called Nyquist's criterion, which states that if the signal shape is obeying a particular property, then we can recover the signal at the receiver without having any intersymbol interference. So what does it say is that the signal P of t should have the property that it should be 1 at t equal to 0, and it should be 0 at all other t's. That is, for odd, that means, say, so what happens is that a stream of zeros and ones are coming at the transmitter. So once you will assign a shape, say it's called pulse shaping filter, and you send it through a channel. At the receiver, there is another filter, say usually it's a matched filter, and the filter at the receiver's output is sampled at every TS instant. So to avoid ISA, what the Nyquist say is that at the sampling instant only the required signals component should be present. All other all other all other things should be zero. That means the pulse shape should have regular zero crossings at the sampling instance. So this criterion P of t equals 1 at t equal to 0 and 0 at all other t's. I can write this as summation over n varying from minus infinity to infinity p of nts del of t minus nts, which is, so if you look at this is like an impulse, right? So this I can write it as del of t. Are you agreeing with this?
But there is P of NTS.
See, p of nts according to this Nyquist criterion, when will p of nts has value? Only when n equals 0. I can either write it as, see, p of nts, this I can write it as n equal to 0. So p of nts will be having a non-zero value only at n equal to 0, right?
Yes. Right.
So this is true, right?
Yes.
Okay. All of you are agreeing with this?
What is P of T?
Okay, P of t. See, P of t actually this entire thing. See, channel is also having an impulse response, say h of t, right? So say this is some pt and this is some ht. This is some other pr. So p is actually the convolution of pt, ht, and pr. Okay. So what exactly uh, this this means is that a- at the receiver while I am sampling, my signal should be in such a way that I should get only the value that is at the instant. There should not be any component from any other signal. So actually P is in fact the convolution of these three impulse responses. Ramesh, is it clear?
Yes. Okay, madam.
So now come to this condition. If I take the Fourier transform of this, I will get 1 by Ts summation over n varying from minus infinity to infinity P of f minus nfs equals 1. This I obtain by taking the Fourier transform. So fs is actually what? 1 by Ts, right? So this condition I can write it as summation over n varying from minus infinity to infinity P of f minus n by Ts equals Ts. Did all of you follow this? Did all of you follow this? Please respond. Okay. So I hope everything is clear to you up to this point. So to see which symbol is offering zero ISI, we need to see the pulse shapes that is satisfying this property. So the pulse shapes satisfying this property give zero ISI. Okay. So we need to in the question we are given four options. So we need to see which of these four pulse shapes satisfy that property. So one thing I need to tell here is that in the question, like if you are actually following this condition fully, no option satisfies this condition. Like that means out of these four options that is given in the question, there is no pulse shape that is satisfying this condition if you take it as it is. Instead, if I am looking this condition as summation over n varying from minus infinity to infinity, P of f minus n by Ts equals constant. If I am taking this condition as instead of Ts, if I am taking the right hand side to be a constant, that means whenever if I shift the pulse and then if I take the summation of that, the amplitude level, if the amplitude level remains constant, then if I take the condition to be like this, then I will get an answer. So the answer in the answer, like in the gate answer key is according to this second criteria. Okay. So let's look at the options one by one. Let's take the option A. So P of f is a rectangular pulse. Okay. So here, okay. Before that, we need to calculate what is Ts, right? Because see, we are shifting by, okay, we need to calculate actually Fs. So Fs is given as 2000 symbols per second, right? So Fs is 2k. So what we need to do is we need to shift this P of f by P of f minus n to k and see whether its amplitude is constant. Okay. So take the first signal. Shift it by 2. Since the x-axis is in kilohertz, I just need to shift it by 2 and see whether its amplitude is 0. So when I shift it by 2, the shifted version and the original version gets overlap. There is an overlapping in this region, right? So there will be so many pulses like this. So there is an overlap in a small region, right? Are you guys okay? So see in this particular region, its amplitude will be higher, right? Because see it is getting overlapped, it is getting superimposed. So in this particular, say this width is having a higher amplitude, right? So will this pulse satisfy this condition?
No.
Okay. So this pulse, if we use this pulse, we will not get 0 ISI at the receiver. So this is not an answer. Now let's take option C. Okay. So option C is
Ma'am, I didn't get why not the option. Can you please?
option A. Okay. See, when you shift this P, like I am explaining option A, okay? So when you shift this P of F by 2, so consider P of F minus 2k, okay? When you shift the signal, see, it's, okay, yeah. See, this edge will come here, right? It will come at point 0.8, right? And this edge will go to point 2.4. Sorry, 2.2, right? So the signal is between point 0.8 and 2.2, right? Trilogen, are you agreeing with that? Sorry, 3.2.
3.2.
Yes, ma'am. Yes, ma'am.
So in this region there is an overlap, right? So its amplitude, so that means those two signals are getting superimposed. So in that particular region, the amplitude goes higher, right? So this that won't be a constant, right? So its envelope will be something of this form, right?
Got it.
So that is why
So
it
the
is not
value of the
yeah, particular.
value of the amplitude increases.
Yes, correct. So now come to option C. Okay, shift this signal P of F by 2k. So what happens here is that here also this thing will come at point 0.8, right? So here also there is an overlap.
It should be before 1, right?
Yes. Okay, sorry. Yeah. So here also there is an overlap, and in this region, C, again the amplitude gets added, right? This particular region. So again, this pulse shape is not satisfying the Nyquist criterion. Are you guys agreeing with that?
Yes.
Okay. Now, now come to option B. Okay. So here also shift the signal by 2K. So here also you could see that it comes to minus 1.2, 1.8. Okay. So here also see, here you need to be very careful. Here these two things will not add up to one, right? Because here this is having a this is here this height is this. So you can actually sometimes see when you have overlaps like this in these particular regions, these two and these two gets added up, and you'll get this line, right? If the signals were having overlap like this, in this particular region it will be like this, right? Are you guys agree with that?
Yes.
But when you come to this example, it is not the case. Here see this amplitude and sorry, these two things actually will not get added up to this value, right? Because it's not overlapping at the correct position. So this option is also not satisfying the Nyquist criteria. But instead, if it is having a width of say zero point 0.8, will it instead of 1.2, if it is having zero point 0.8, will it okay not zero point 0.8, 2 itself. So if it is having a different width, not 1 point, my 1.2, okay, if it is having 2 itself, will it satisfy the condition?
Yes.
Okay, so since it's not having the correct width, it is not satisfying the condition. Now come to this example. Here, shift the signal by 2K and see what happens. When you shift this by 2K, minus 1.2 will come at zero point 0.8, right? And 0.8 and minus zero point 0.8 will come at 1.2. So what happens is that it will be having a shape like this, right? So here these two things and these two things gets added and make this amplitude this. Will you guys are you guys agreeing with this? Okay, so here also another P of F minus 2 into 2K will come and shift here. Come and sit here. So here also you will get something, another replica will come and sit here. So everywhere the signal is satisfying the condition. Summation over n varying from minus infinity to infinity P of F minus nfs equals constant. So the signal is satisfying this condition, right?
Yes.
So this is the pulse shape that is giving zero simple interference. See here, the amplitude is 1. If we are taking the condition to be say Ts is what? 1 by 200, right? So then you will find that there is no option satisfying this. But if you take it to be a constant, if you if you take the right hand side to be a constant, option B satisfies that condition. Is it clear to all of you?
Yes.
Okay, can I move to next question? Or should I explain any of this part again?
So sometimes we can take it as a constant if we require. No?
Yeah, true.
It is not ideal case. I mean,
If there are say if there are options with different okay, if there are one second, if there are options with different amplitude, say one is having one is having another value, say zero point 0.5, then you need to take the actual condition p of f minus nfs, summation over n p of f minus nfs needs to be ts itself. You need to go with the actual condition. But since here in all these things every signal is having the same amplitude, so take the condition to be constant and find the answer. Okay.
In option D,
Yeah.
uh, the value between 0 to 0.8 will itself not be constant, right? That is sufficient.
Yes, correct.
Yeah, that's it.
Yeah. 0 to 0.8, correct. Because it will be having some, okay. But what I am saying, what I was trying to say is that say there is one another signal with the same shape, but it is having a different, instead of one, it is having some different amplitude. Then you should actually go with the correct criteria.
Yeah, got it.
Yeah. Neither, do you have any doubt? Okay. Okay, this is a question that is related to not exactly quantization, but which is more or less, because one guy has asked me to solve questions related to quantization. So that is why I kept this question, but it's not exactly related to quantization. Okay, so the question says an analog baseband signal, band limited to 100 Hz, is sampled at the Nyquist rate. The samples are quantized into four message symbols that occur independently with probabilities P1 equals P4 equals 0.125 and P2 equals P3. Find the information rate in bits per second of the message source. So, what the question says is that there is a baseband signal which is having the maximum frequency 100 Hz, and that signal is, that means, say the signal is something of this shape, band limited to 100 Hz. And that signal is sampled at the Nyquist rate. So, what will be the sampling frequency? Can someone tell me that? What will be the Nyquist frequency? Sampling frequency? 200. Yeah, correct. 2f1 equals 200. So, and these samples, that means there are 200 samples in a second, right? Samples sent in a second. So these samples are then quantized into four message symbols. Here you should be very careful that the question says the samples are quantized into four message symbols. Instead of saying that just each sample is represented using 2 bits, it says that it is quantized into four message symbols, and they are giving the probabilities of each message symbol. So that means you are not supposed to take that each message symbol is encoded using 2 bits per sample. sorry, each sample is encoded using 2 bits. You shouldn't take like this. So to find how many bits to find how many bits are used to represent a sample, or average number of bits required to represent a sample is found out by, in information theory it says that if a source transmits symbols from the alphabet, say. Yeah.
Ma'am, here, like we found out that 4 message symbols via that P1, P2, P3, and P4. Ma'am. Like,
Yeah.
know how
Ah.
that each symbol like is encoded by 2 bits.
No. I'm saying that you shouldn't take that sample is encoded using 2 bits. You should not take like that after seeing if the samples are condensed into 4 message symbol. Like we have a common tendency that we will like right away take that each sample is encoded using 2 bits. You shouldn't take like this. That's what I'm trying to say. Okay.
Okay, ma'am.
Instead, we are finding how many bits are required to represent a sample.
Yes, ma'am.
Did you get it?
Yes, ma'am.
Okay. Okay. So to find how many bits are required to represent a sample, we use a fact from information theory. That means if a source is transmitting symbols from a alphabet, say S0, S1 up to Sn with probabilities, say P1, P2, and Pn, then the entropy of the source is same as the average number of bits required to represent a sample. Is it clear to all of you? Is this clear to all of you? Is this point? Okay. So we are given the probabilities. We are given P1 equals P4 equals 0.125. And we are told that P2 equals P3. That means we get P2 equals P3 equals 0.375. Okay. And next question to you. How do we find the entropy of a source? We know that the source transmits 4 symbols with the following probabilities. So, how do we find its entropy?
Ma'am, P1 into log of 1 by P1. Ma'am.
Only that?
Summation.
Okay. So here. So this is the. So whenever you are given probabilities and the symbols, the entropy depends only on the probability mass function, and it is given as summation over I Pi log 1 by Pi. So 0.25. unbelievable. So here I wrote the statement by combining this two and this two because this two and this two P1 and P4 are having same probabilities. Similarly, P2 and P3 are having this probability. Okay, so that's how I wrote the statement. So on calculating this, you will get entropy of source as 1.81125 bits per symbol. That means these many bits are required to represent a symbol in the source. Up to this point, is everything clear to all of you? Nitu, are you having any doubt? Okay. So is it clear to all of you? Okay. So now we are asked to find the information rate, right? Once we found this, how do we calculate the information rate or the data rate in bits per second? We know the sampling frequency. We know how many bits are required to represent a sample in that transmission. So what is the information rate now? F is into number of bits per sample, right? Are you guys following? Did you get what I'm saying up to this point? Okay. So Fs is 200 hertz. We know we have calculated initially. And the average number of bits required to represent a sample is what? 1.81125. So on calculating this, you will get the information rate as 362.25 bits per second. Is the solution clear to all of you? Please feel free to ask if you are having any doubt. Okay, can I move to next question?
Yes.
Okay. This is also a question that is related to this pulse shaping finding bandwidth rate. Okay. So the question says a speech signal is sampled at 8 kHz and encoded into PCM format using 8 bits per sample. So the sampling frequency is 8 kHz and each sample is encoded using 8 bits. So what will be the rate? Can someone tell me that? What will be the rate?
64.
Okay, right. 64 kilobits per second. Now, the PCM data is transmitted through a baseband channel via 4-level PAM. The minimum bandwidth required for transmission. See, initially, okay. Initially, in the first question, we have seen that we transmit the say this PCM data in the question. It says this PCM data is transmitted through a baseband channel via 4-level PAM, right? So in baseband channel, like we transmit this each bit using some shape, right? Pulse. Sometimes we may use rectangular or sometimes we may use raised cosine. So we use this pulse shape to transmit the bits using the through the channel, right? So in the question it says what is the minimum bandwidth required for transmission? So in the pulse shape in the pulse shaping part, it says that the pulse shape that takes minimum bandwidth is the sync pulse. Okay, so we have seen that, see, when while transmitting we need to also ensure that there is no intersymbol interference. So the pulse shape that satisfies that criterion and that satisfies that criterion and it takes minimum bandwidth is sync pulse. So in the question it says what is the minimum bandwidth of the sync pulse that is required for transmitting these many kilobits per second through the channel. So in the low pass signal, if a signal is having maximum frequency component fm, what is the sampling frequency required to avoid aliasing? What is the minimum?
2FM.
2 fm, correct. So these many samples will be there, right? If we sample at the minimum sampling frequency itself, these many 2 fm samples will be there, and this 2 fm samples I am transmitting through the channel using a 4 level PAN. So how many bits are used to represent a sample?
2.
2, correct. So instead of fm, let me write it as bandwidth itself. Okay, so 2 times bandwidth into log 4 to the base 2. So these many bits I am transmitting, right, through the channel. But in the question we got the rate from the initial data that is given. This rate is actually 64 kilobits per second. Okay. Is that clear?
Yes.
So bandwidth will be what? 64 by 2 into 2, which is 60 kilohertz. Is it clear to all of you? Is this clear to all of you? Or should I explain it again?
So you're telling that the rate at which the data rate is 64 kbps.
Yes.
Yeah. And the data is being transmitted using 4 PAM symbols. Hence, what is the minimum bandwidth?
Yeah. So baseband channel means, see, there will be a pulse shaping associated. So the minimum bandwidth means the minimum bandwidth of the pulse shape that is used. That is actually it meant. Okay. Is it clear, Sadar? Okay.
Yes.
Okay. So can I move to next question? We'll see one more question and we'll wind up the session. Is it clear to all of you? Can I move? Okay. So this was a question that I discussed in one of the previous classes. So if anyone who has attended that class in the phase 1 part, you can leave. You are free to leave. But I will discuss this question because this question is closely related to the question that we have seen right now. Okay. So the question says an ideal bandpass channel 500 Hz to 2000 Hz is deployed for communication. A modem is designed to transmit bits at the rate of 4800 bits per second using 16 QAM. Find the roll-off factor of a pulse with a raised cosine spectrum that utilizes the entire frequency band. Okay. So see, initially we have seen that the channel is, like initially I have told in the first question, the channel is always band limited. So the question says the channel is a bandpass channel over 500 Hz to 2000 Hz. So what will be the bandwidth of the channel?
1500.
Correct. And a modem is designed to transmit bits at the rate of 4800 bits per second using 16 QAM. So The data rate is 4800 bits per second and it is transmitted using 16 gram. So, to get this data rate, that means each sample is represented using 4 bits, right? Because we are we are sending the signal using 16 gram. That means there are 4 bits, right? Each 16 gram symbol is composed of 4 bits, right? So this data rate is obtained by this, right? 4 bits per sample into sampling frequency. This is how we obtain this data rate. Are you guys agreeing with this?
Yes.
Okay. So first we will obtain it as 1200 hertz. Okay? Or 1200 samples per second. Now, we are asked to find the roll-off factor of a pulse with a raised cosine spectrum that utilizes the end frequency band. So, we today we have seen so many questions that uses various pulse shapes, right? So, this question uses a raised cosine spectrum. So, the raised cosine spectrums look something of this form, okay? And this is given as 1 minus alpha fs by 2, where fs is the sampling frequency, okay? And this end is given as 1 plus alpha fs by 2. Okay, this is a raised cosine spectrum. And what is alpha? It is the roll-off factor of the pulse. Is it clear to all of you up to this point?
Yes.
Okay. See, now consider this raised cosine spectrum as a signal. So, what is the bandwidth of the signal? If you consider this raised cosine spectrum as a signal, say x of t or something, what is the bandwidth of the signal? 1, is it 1 plus alpha? Bandwidth is C. Bandwidth is, since it's a low pass signal, right? So its bandwidth is 1 plus alpha by 2 fs, Hariprasad. Because see, when you consider a low pass signal of this form, we say it is FM, right? So this is, or let me frame a question in a different way. What is the maximum frequency component in the signal? It is 1 plus alpha by 2 fs, right?
Yes.
Okay. So if you want to sample a signal of this FM, what is the sampling at how much sampling frequency you will sample?
1 plus alpha fs.
Correct. So this is okay. This is FM. Okay. So the sampling frequency that I will use will be 1 plus alpha fs, right? But I know the sampling frequency that is being used. Okay, sorry. Okay, sorry. So 1 plus alpha, I know the sampling frequency, this fs. So see, these many see, the channel is having a bandwidth of 1500 hertz, and our question is the raised cosine spectrum. What is the roll-off factor of a pulse that with a raised cosine spectrum that utilizes the NDA frequency band? So see, the channel can take 1500 samples in a second, right? Are you guys agreeing with that?
Yes.
Okay. Our sampling frequency fs, we have got it as, see, fs is this fs, okay? We have got it as 1200 samples per second. So, if you are using this pulse, raised cosine pulse, how, if I sample it at the sampling frequency 1 plus alpha fs, these many samples I can send it through the channel, right? These many samples I can send it through the channel. Are you guys agreeing with that? Did you follow this step?
Yeah, go ahead.
Okay. See, so it says I'm utilizing the entire channel spectrum. That means I will equate this 1 plus alpha fs equals 1500. Okay. So fs I know, that is 1200. So this I will get it as 5 by 4. So alpha I will get it as 1 by 4. So 0.25 is the roll-off factor that I should use in the raised cosine, so that I will utilize the entire channel bandwidth. Is this clear?
So how can you relate bandwidth to samples? Isn't bandwidth
See.
related to bits?
See, bandwidth. See, when I say 1500 hertz, that signal, that channel can occupy that many, that many. Say, see, fs. When I say fs is 1200 hertz, what it means? I will be sending 1200 samples per second. That's what it meant, right?
Yes.
So when I say my bandwidth of the channel is 1500, it can accommodate maximum 1500 samples. Okay.
Okay.
So when I use a signal of this form, my sampling rate will be 1 plus alpha, this thing, right? So that, see, this is a band limited signal, so that if I use something greater than this, like if my 1 plus alpha fs greater than 1500, anyway my channel will induce distortion, right? Because it cannot accommodate more than that. So only thing, 1 plus alpha fs should be less than or equal to 1500. I can either underutilize my channel or I can utilize it to the fullest. Is it clear?
Yeah. So roll-off factor, that is a maximum value or minimum value?
See, so this is the 0.25 is the 0.25 is the roll-off factor that utilizes this channel bandwidth fully. So if I use something less than this, I will get 1 plus alpha fs to be something less than 1500, right? Say,
Okay.
so I won't be utilizing my channel fully. Or,
And if alpha goes beyond that, then you'll be going over the capacity.
yeah. Or if you're having other problem, as Hari Prasad pointed, you can take the bandwidth to be something of this form. Bandwidth to be twice 2fm. Something. See, you are sending it through a bandpass channel, right? So you can take the bandwidth to be 2fm. Okay? And then equate it to 1500 if you're having doubt. Like in the initial way that I.
Oh, no. That was not a problem.
Okay.
Yeah, and by roll-off factor, you mean the actual roll-off factor of that curve, right?
Yes.
Or the same thing?
So is it clear to all of you?
Madam, hello.
Finish.
Can you say something about the raised cosine spectrum, madam?
Okay. Raised cosine spectrum. One that okay. So this is see, in the previous question I have told that sync pulse is the pulse shape that uses the minimum bandwidth and satisfies the condition that summation over n p of f minus nfs equals case, that zero ISI condition. So that is a pulse shape that is having minimum bandwidth and satisfying that condition. You can create so many pulses that satisfies the zero ISI condition, right? Ramesh?
Yeah. Yes.
But the simples is the one with minimum benefit. But there are some disadvantages that is having with simples. Say you might have been heard that the decay is very slow, and it's hard to those and it's hard to realize. So those things are some of the disadvantages with simples. So instead, we will go with other pulse shapes such as raised cosine spectrum, which this pulse will satisfy the zero ISI condition. Okay, and it is
Both the sync pulse and the riser cosine spectrum both
yes,
are
yes.
having ISI, right?
Yeah,
Both.
if both will eliminate ISI at the receiver. It will also satisfy zero ISI condition, and it is defined like this. Okay, 1 minus this point to be 1 minus alpha fs by 2, and this to be 1 plus alpha fs by 2. Okay.
So x-axis is a frequency, madam.
Yes, yes, yes,
Okay. So alpha is a roll-off factor, right?
yes.
Okay. Okay.
That determines this slope or this decay. Okay.
Okay.
Neetu, are you having a doubt?
Ma'am, what is the reference for this?
Reference. Okay. Reference. There is one NPTEL lecture, Principles of Digital Communication by Professor Surendra Prasad. I think it's a video that was recorded like maybe 10 years back. But he explains everything very in like very detailed in a very detailed manner. Okay.
Ma'am, Professor?
Surendra Prasad, IIT Delhi.
Thank you.
Yeah. Okay, with this question, I am winding up today's session. So, if you are having any doubt, please feel free to ask. Otherwise, you may please leave. Thank you all for attending.
Thank you, ma'am.
Thank you. Yeah.
Next week also, are you solving on communications or signals?
Signals and system.
Okay. Is it Z transforms or Fourier transform?
No, I haven't decided. But if you have any specific question, I can take it.
Okay. In 2019 paper,
Okay.
IIT Madras, there was a question on
Hmm.
Z transform
Okay.
related to pole zero concept.
Related to?
Pole zero concept, yeah.
Okay. So, which is having pole inside? Is that the question?
Yeah.
Okay.
Have you already solved it?
No. But I have seen the question. So, if you are not having any doubt, you can leave. Thank you. all.
Thank you.
Yeah.
Thank you, ma'am.
Thank you. Sneha, Ramesh, Trilochan. If you are not having any doubt, you can leave.
Madam, that any book for digital communication?
Okay, any book for digital communication? Some topics you can refer to Simon Higgins, but I think you can refer to these NPTEL lectures. That will be like that will be enough for you to solve these questions. I feel.
Okay, Simon Aiken.
Simon Higgins, you can refer because see, when you refer to a book, you need to sit and read and understand. But when you listen to a lecture or a class, it will be more easier it will be more easier and faster to cover the topics, right?
I understand.
Yeah.
Thank you, ma'am.
Yeah. Thank you.